Well, continuing in section 4.6, we mentioned in our previous section that the solution set, so the solution vectors, that set of all the solution vectors of a homogeneous linear system of equations is a subspace. So you might say, hey, maybe the set of the solution vectors of non-homogeneous is also a subspace. Well, guess what? That ain't never going to happen. And it's very simple to understand that, because how could you possibly have the zero vector? If all the variables equal zero, then how's it going to equal anything other than zero? So the only way you're going to have the zero vector is when you have a homogeneous, not a non-homogeneous. But there is a fascinating relationship, a lot of stuff that we can learn, and connections and so on and so forth. So let's get right to it. The solutions of a non-homogeneous linear system, if xp, x is a particular solution of the non-homogeneous system of equations, then every solution of the system can be written in the form x bar, or x, I should say. X is the vector, equals xp plus xh. And what is xh? Xh is the solution of the corresponding homogeneous system ax equals 0. So again, we're looking at the set ax equals b, and we're saying that this has a solution, let's say at least one solution, and at least one solution, and or maybe not, I don't know. Anyway, we're looking at this set, and if xp is a particular solution, so it has obviously xp, then any solution can be written as take my xp plus add on xh, or xh is a solution to the. Now, those of you who took, you may remember that we have a similar situation in differential equations. In differential equations, you had the particular solution of the differential equation plus the homogeneous, the solution of the corresponding homogeneous differential equation. So this is very similar to that. And why? Because when in a typical first semester differential equations course, the focus is on linear differential equations, and this is a fact in linear differential equations. Get it? Linear differential equations, linear algebra is a big connection. So the proof is really simple. Let's say x is any solution to ax equals b. So the x vector is any solution. So if I look at the vector x minus xp, well, that's going to be a solution to the homogeneous system. Why? Because a times x minus xp, I could distribute. That's ax minus axp. But ax is equal to b, and axp is equal to b. We're saying that these are solutions of the non-homogeneous, but b minus b equals 0. So basically, that means that, which means that x minus xp must be a homogeneous solutions. So we're going to call that xh, and that's equal to x minus xp. So therefore, x is equal to xp plus xh. Ta-da! And very, very simple proof. Is that awesome? A lot of times these proofs, it's funny how in linear algebra, sometimes you have these proofs which have these gazillions of algebra steps and substitutions and all kinds of stuff. And sometimes these algebra proofs, they go just lickety split. So you never know. Anyways, we want to find the set of all solution vectors. Let's look at an example of this. We want to find the set of all solution vectors of this system here. So this, as you can see, is 4 variables and it's 3 equations. So we want to find the set of all, and it's not homogeneous because you have 5, 8, negative 9. We want to find the set of all solution vectors. So, oops, went too far. So we look at we're going to write the augmented matrix. So we're going to take all these coefficients and the constants and make this big giant matrix here. So everything up to the first 4 columns are that's the coefficient matrix, and then the last column is the constant matrix. That's the B. And if we do some some row reduction, some elementary row operations, we can reduce it down to this sucker right here. And notice that I have a whole row of zeros on the bottom, which is cool and awesome. And I have a leading one over here, and I have a leading one over there. I think I'm going to highlight the leading one because we're into that now. Let's highlight this leading one. Boom. And let's highlight that leading. Oops. Let's highlight this one. Let's highlight that one. And so we have these two leading ones. And and that means that I have two columns left over. This column of constants doesn't count, but these two columns here are left over. So the last column will make the parameter t, and the next to second to last column will be the parameter s. And we're going to get, so x4 is t, x3 is s, which means that our vector, our solution vector, is going to look like this. So x1, x2, x3, x4, these are the solutions. So it's going to be 2s minus t plus 5, negative s plus 3t minus 7. This is just s, and that's just t. And again, how do I get that? I get that from these equations right here, because that's my t, that's my s, and I using the s's and the t's, I bring everything over to the other side, and pow, that's what I have. Now, I could separate this out into the s, I'm going to call it the s vector. That's not really what it's called. I'm calling it an s vector. The s vector, I'm calling it the t vector, and here is just really just a constant vector. But that means that the solution is s times this u1 vector. U1 is just the 2, negative 1, 1, 0. U2 is negative 1, 3, 0, 1. So this is an infinite amount of solutions. And then I have the xp. The xp is really just the 5, negative 7, and 0. So, meaning that if x, which means that if I would just ignore the parameter, if I, how do I say this? If I would just plug in 5, if I would just plug in x1 equals 5, x2 equals negative 7, x3 and x4 both equal 0, and plug that into the original equation, so I would get here 5 equals 5, 15 plus negative 7 minus 0 equals 8. And here I get 5 minus 14 minus 0 equals negative 9. So if I would just plug in 5, negative 7, 0, 0 into the original system of equations, I would get the actual non-homogeneous solution. If I plug in these guys, if I plug in these guys with s and t being whatever I want, I would get I would just get 0, which because that's the solution of that. This part would be the solution of the non-homogeneous of the homogeneous part, and that, my friend, is the story. So every solution is of this form. This is my xp, and this is the xh right there, and every solution is in that form. I think I'm going to actually even make it more explicit. So let me just pause this while. Now, this next theorem here is pretty straightforward. It's pretty common sense, really, and we'll see the proof is pretty simple. Ax equals b is consistent. Consistent means it has a solution, as opposed to sometimes there's systems of equations that don't have any solution. Sometimes there's no solution. So it is consistent, meaning it has solutions, if and only if b is in the column space of A. Now, this is a very fancy way of saying something that just makes a lot of sense, because A times X, now AX equals B, right? Well, that's our equation. AX equals B. So, but AX is these coefficients times this big vertical vector, this column vector. But we learned that you can, when you do this multiplication, it winds up being x1 times the first column, x2 times the second column, dot 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 xn times the. We actually discussed this when we did way back when we did matrix multiplication. But just to remind you, when I would do the multiplication, I would get a11 x1, a12 x2, down the line, a1n xn, and so on and so forth. So really, it's always the first term in each row that multiplies the x1, the variable x1. And when I say in the first term of each row, that means the first column, which means I wind up getting x1 times all the first column numbers, and I'm going to want, and my x2 the x2 over here is going to multiply. These guys in the second column are the only ones that are actually going to multiply in x2. So I want to x2 times all these guys and say, and that's kind of, again, we kind of explained this. I'm explaining it quickly, but we kind of explained this back, back when. Anyway, but what is this? These are all the coefficient. These are all the column vectors, and the x1, x2, xn are just different scalars. So basically, this is a linear combination of this by definition, everything over here, all the way on the right side here, is by definition a linear combination of the column vectors, which is what it means to be part of the column space. So if ax equals b, that means b is going to be a linear combination of these column vectors. So it's pretty, really just makes a lot of sense. So let's look at an example here. Suppose we have the system of linear equations, and we have a system of linear equations here. X1 plus x2 minus x3 equals 1. Again, we used to, instead of saying x, in high school, you would say x plus y minus z equals -1. But instead of, but since we could have, in theory, we have 4 variables, 27, 27 variables, you run out of letters, what I'm saying? So we just say x1, x2, x3, these are variables, equals -1. This would be x plus z equals 3, and so on and so forth. So what we're going to do is going to write the augmented matrix. So here, the first 3 columns is the coefficient matrix. The last column is the constant matrix. Now, if we do our row reducing magic, we wind up with this right here. And again, let me just highlight this. Let me highlight this and highlight that. These are the leading ones. It's nice to highlight the leading ones so you can see it more clearly. Which means if I let x3, the third variable, if I let that equal t, and I bring this stuff over to the other side, I get x1 is -t plus 3. X2 is going to be 2t minus 4, and x3, as I said before, is just going to be t. So this gives me this gives me all the solutions. So B, as B is in the column space of A, and the system of linear equations is solutions is consistent, and everything works. Yay! And now, finally, this is I'm very proud to present this. We made a list of conditions, of equivalent conditions for square matrices. And if you notice, we've continually been adding to that list. We had like 4 things and 5 things. Well, now all of these things are the same thing. These are all really different ways of saying the same thing. I'm gonna make it nice and big so we can all see it nice and big. Let's look at them all. So A is a square matrix, it's an n by n. So to say that A is invertible is the same thing as saying AX equals B has a unique solution, and is the same thing as saying AX equals 0 has only the trivial solution. And it's also the same thing as saying A is row equivalent to the identity matrix, the IN, which is the n by n identity matrix. And it's also equivalent to saying that the determinant of A doesn't equal 0. We've seen all 5 of these before. It's also equivalent to saying that the rank of A is equal to n. And remember, the rank was the dimension of the row space and or the dimension of the column space. And it's also equivalent to saying that the n row vectors of A are linearly independent. And it's also equivalent to saying that the n column vectors of A are linearly independent. So any one of these, if any one of these is true, then all 8 are true. These 8 conditions. And if any one of these is not true, then all 8 are not true. So these are if and only if. It's an 8-way if and only if. And that, my friends, is the end of 4.6, as you can see right here. And I'm actually going to what's the word? Oh, there's going to be an augmented section, meaning I'm going to add some more videos, just going through some of these things by hand. And that concludes this video, and we'll see you next time around.